Hello everyone, we're going to learn 4.3 in this class. It's called subspace. So before we do subspace definition, I want to give you some idea what the subspace means look like. Okay, subspace actually is a vector space. Firstly, for example, we have a vector space which is Rn. Okay, I can just draw like this, or we can say R2. So just give you some idea. We have a vector space and we have a subset. Firstly, subspace has to be a subset, a smaller set in Rn. For example, we say S. And if it's closed under scalar multiplication and addition, so that means if we have two vectors and if we add them together, U plus V still belongs to S, and the scalar multiplication is also in S. It doesn't go outside. Okay, it's still a vector space. So it's like, what is subspace? Firstly, subset. Okay, it's a subset, smaller set, and closure under scalar multiplication is like scalar multiplication, we just write on this, and addition. Closure means those two still belongs to S. Okay, that's the subspace. That's the meaning. Now let's take a look at the formal definition. Definition 1. Let S be a non-empty subset. Firstly, it has to be a subset of a vector space V. Okay, and if this S is itself a vector space under the same operations of addition and scalar multiplication. Addition and scalar multiplication as used in V. Okay, then we say S is a subspace. This definition for the subspace of V. Okay, so let's take a look. There is theorem. The theorem says S is a subspace if and only if subspace of V, if and only if, that means if and only if S is closed under addition and scalar multiplication. And addition. Okay, so closed means what? Closed means I don't know, do you know what's the, for example, this means belongs to, this symbol means belongs to. Okay, U belongs to S, so if V belongs to S, so the addition still belongs to S, still inside S, and the scalar multiplication also inside S. That means closed. Okay, that's the meaning of closed. Don't worry too much. I know this look difficult right now, but let's take a look at example. After we do some example, you will have some idea what's the meaning of this one. We can take a look at this one. Okay. Let's see. We have S, which is given by all the vectors, which is x1, x2. And this vector, definitely, we know this vector is in R2, right? Okay. Okay, and all the xi, x1 is greater than 0. So that means what? That means the vector, they are all in 2D, like in R2, but x1, that means first component has to be positive. So it's kind of like this. This is like a subset, definitely. It's only the right side of the whole plane. Whole plane is R2, xy plane, but we need the first component. That means you can look at this as x and y. So that means all the x are positive. Right, first component positive, so that means the right side plane definitely is subset. And let's see, is this closer? So we can pick any two vectors. For example, we can pick a u vector, which is x1, x2, and a v vector, which is y1, y2. Is that okay? y1, y2. And they both belongs to S. We pick any two vectors in S, belongs to S, and because they are in S, that means x1 is greater than 0, means y1 is greater than 0. Right? That's what is given. Now let's take a look at the sum. We want to see if the sum is still belongs to S or not. So if we do the sum, xy 1 plus y1, x2 plus y2. This is the sum of two vectors. And we noticed that x1 plus y1, that means the first component. Because x1 and y1 are both greater than 0, the sum definitely is greater than 0. So this vector, you can see this vector is inside S because it satisfies the conditions for the subset S. The first component is positive, right? Next, let's try the scalar multiplication. So, which is k, x1, x2. And if we do scalar multiplication, kx1, kx2. And here, we don't know k is positive or not. Because k, this number, if k is negative, this number can be negative. That means this vector may not inside S. It may go outside. So here is like a, so it may go outside to the S, to the left side. You can see left side of the plane. So it may go outside. In this case, this S is not a subspace. You know what's the meaning of subspace? Subset that closure under addition and scalar multiplication. Okay, let's see. Here, let's do another example. Example 1. Verify that the set of the linear system is a subspace in R3. That the set of all real solutions to the following linear system is a subspace. In R3, let's take a look. We have a linear system is given by two equations, three unknowns. Do you remember how to solve this linear system? Okay, this is homogeneous linear system. So let's see how to solve it. When we solve this, we write down the augmented. We are going to use Gaussian elimination. Okay. Gaussian elimination, that means we change the augmented matrix into row echelon. So 1, 2, -1. So this is the coefficient matrix, right? And we also need to add the b. So the constant b here are all zeros. Firstly, we write down the augmented matrix and we reduce this into row echelon. So it should be easy to do this problem. Row 1 times -2, add to row 2 times -2, so -4, add there 1, times -2, +2, add there -2, and here's do 0. Is this row echelon? Yes, we have leading 1, right? So who has leading 1? You can see. Actually, how many unknowns do we have? We have 3 unknowns. And x1, x2 has unknowns. So has leading 1. So we can see here who can be the free variable. So we set x3 to be the free variable. It's like t. x3 equals t. Let's solve for x2. x2 equals what? So actually x2, from the second row, you can see x2 minus 2x3 equals 0, right? So in the future, you can just look this as the second row as equation. When you move, you change this to positive 2t. So positive 2t. So x1 equals -2x2. Okay, I can do this next step. 2x2. I'm looking at the first row now because I'm solving for x1, and plus x3 and plus 0. So plug in x2 2t and x3 t. Simplify, which is -3t, -4t plus t, -3t. So let's see what is our solution. Our solution x1 is -3t, x2 2t, and we have x3, which is t. We had to write down them in order, right? x1, x2, x3. And this is the solution. But for the solution set, what do we write? For the solution set, we write down usually like this way. Okay. X, the solution, belongs to R3 because it has 3 components. And then let's see what's the condition. All the x should satisfy equals this one, -3t, 2t, and t. Okay, we are going to this example. We want to verify the solution set. Okay, the set of all real solution is subspace. So firstly, we need to find the solution set. So here is the solution set. It's kind of review what we did in the last chapter. In chapter 2, use Gaussian elimination to solve linear system. Sometimes the linear system has one unique solution. Sometimes it may have infinity solution. And in this case, it has infinity solution. We have free variable. Right? So here's the solution set. Next, we want to verify this solution set. This is a subspace of R3 because it belongs to R3, but all the solution belongs to R3, but it has to satisfy this kind of condition, like -3 to 1 times t, right? Has to satisfy this condition. Now let's just pick any 2 vectors. So we can pick like an x vector, we can pick a y vector. So for x vector, we can use -3t, 2t, 1. And for the y vector, we can do s, just do different vector, but similar thing. It also has the same form, but we change into another, just different letter, right? So we have 2 vectors, and they all belongs to S because they have the same kind of form. And next, we want to test our goal. We want to see if this and this still belongs to S or not. Okay, we want to see this because we want to see S is closed under addition and scalar multiplication. Let's do the addition. If we add x and y, can I just, look at here, we add them together at corresponding exponent, right? So negative 3t minus 3s, 2t plus 2s, and 1 plus 1. Is that correct? And simplify a little bit. Negative 3t plus s, 2t plus s, and the last component is number 2. I'm going to ask you, is this vector still belongs to S or not? Belongs to S or not? Definitely not, because of the last component. The first two, they satisfy this kind of form, negative 3 and times 2 and 2 times that one, right? But last one, they both are good, but the last component is number 2, doesn't belong to S. So in this case, we can say any two vectors in S, but when we add them, it go outside of this set. So S is not a subspace. Right? So this is the first example. Let's take a look at exercise problem. S equals this one. X belongs to R3, is still a subset in R3, and X equals what? R. Okay, let's do easy one. Okay, this may be a little bit complicated one. So I'm going to give you R2. And all the X in R2 satisfy this T, 5T, and all the T are real numbers. Okay, so let's say if S is a subspace or not. Or we can see whether S is subspace. Okay, let's take a look. Please try this by yourself. And here I'm going to give you the solution. I pick any two vectors in S. So I just pick any two vectors in S. So I'm going to make them T, 5T, the other one S, 5S. And we do the addition. T plus S, and the other one 5T plus 5S, but I can simplify, factor the 5 out. And I noticed it satisfies the same form, T, 5T, right? So just like a second component is 5 times the first component, satisfy the form. So this belongs to S. Let's do the scalar multiplication. It's going to be K times T, 5T, and equals KT, 5KT. So this also belongs to S. In this case, we can say S is a subspace of R2. Okay, just like this kind of thing. Not difficult, right? Don't worry too much. Let's take another one. I'm going to give you another exercise problem. So we want to verify this set is given by R2. Like in R2, X equals what? R negative 3, R plus 1. Similar to our exercise 1, okay? And R belongs to R. All real number. We want to verify this is not a subspace. of R2. Let's try. You can try this by yourself. We always want to pick any two vectors in S and see if S is closed under the addition and multiplication, scalar multiplication. I'm going to give you the solution here, but I suppose you already did this by yourself. If you already know how to do this, you can skip this. X belongs to S. I'm going to write down y t negative 3t plus 1. Then I do the addition. R plus t and negative 3 R plus t. So I simplified plus 2. So you can see here it's become plus 2, but original it should be plus 1. So this doesn't belong to S. This is not a scalar. Is not a subspace. Here I use the addition, but you can also try scalar multiplication. If you do this scalar multiplication, you will get kr negative 3 kr plus r. So same thing here, plus k, sorry, k, because k can be anything. Definitely this doesn't belong to S, right? You don't have to, because it's already, it doesn't satisfy one condition, so we don't need to test the other one. If it satisfies the first one is closer under addition, then we test the scalar multiplication. It has to satisfy both conditions. Now let's do example 3. We want to express a set in, like learn how to express set notation. So let's see. As in set notation. Let's see. If we have a vector space which is R2, and what is S? S is the set of all vectors, all vectors x, y in the vector space, and satisfying this condition, 5x plus 2y equals 0. Okay, so let's write down the set. Let's write down set S in set notation. Okay, let's see how to do this kind of thing. We can, all the vectors satisfy this condition, right? That's the first component, second component. We can solve for y here. So like solve for y. Let's see, y should equals to negative 5 over 2 x, because we move 5x to the right side and divide by 2, right? So this is y. So let's write down all the vectors. So the vectors write down should be look like x, and what is y? Like this one. Is that right? All the vectors should have this kind of form, x and y. So let's try to write down s. S equals to what? All the vector belongs to R2, and all the vector has which form? Has this form. X negative 5 over 2 times x, and x belongs to R. So this is the set notation. Let's try this one. Same thing. If we say the vector space is still R2. Sorry. So negative 3x plus 4y equals 0 satisfy this condition. Let's write down the set notation for this. So I'm going to write down this way. We can try to write down. All the vectors still belongs to R2, and all the vectors equals to what? X, 3/4 x, and x can be anything, just like this. let's try another example. Okay. Example is about a subspace, but right now you can see what is S. S is different. It's not in R2, R3. It's going to be a set of all the matrices. Let S denote the set of all symmetric matrix. Think about what's a symmetric matrix. What's the meaning? That means transpose is same as itself. Okay. Verify that S is a subspace of MNR. So what's the meaning of this one? MNR. This means M means matrix. N means N by N order, and R means all the elements belongs to R. So this means all the N by N matrix, and it's also the real number. In the future, you may see like this. What's the meaning of that one? So this means 2 by 2 matrix, but all the elements may in the complex. So for example, 0, 2i minus 1 can be complex number, something like that. Now let's take a look at how to. Firstly, we want to denote S. S is the set. Okay, denote the set of symmetric matrix. So we want to verify S is a subspace. So firstly, let's write down S as set notation. Right now, it's going to be set of all the matrices. So we write down like, it's same as like before we say all belongs to this one. Okay, R2. So here we do A as matrix. All the matrix belongs to this vector space. And let's see, what's the condition A satisfy? A satisfy what condition? It's symmetric. Symmetric means transpose equals itself. So what's the symmetric? It's like 1, 2, 3, 3, something like this. And if we look at 3 by 3, so if 1, 2, 3, so here -1, -1, 4, 4, and here 5, 5. This is called a symmetric matrix, right? So they are the same thing, okay? Same thing. And you can see the transpose of this kind of matrix equals itself. That's also the definition of symmetric matrix. Now we want to verify this is a subspace. So we want to see if S is closure under addition and scalar multiplication. Now we need to pick any two vectors in S. So we pick any two matrices. Is that right? And we want to see if the sum still belongs to that or not. Okay? Firstly, we pick the sum, and we want to see if the sum is still symmetric or not. We do the transpose. And this is the property, A plus B transpose equals A transpose plus B transpose. And because A, B all belongs to S, they are all symmetric, so AT equals A and equals B. BT equals B. So you can see A plus B transpose equals A plus B. That means A plus B belongs to this S. Next thing, K, we can take that out. AT, and which is K times A. So you can see KA transpose is same as KA. So we say KA also belongs to S. So we say S is a subspace of MNR. Okay, can you see what's the meaning of subspace now? It's more general. It's not just R2, R3. It can be matrix vector space.